Okay, so welcome to Math 150, Section 2, Lecture 20-ish. So as most of you hopefully know, spring registration is coming up soon, where you have to decide what classes you want to take. So I want to give you a sense of where this material leads to. One of the advantages of having this as a flipped class is we have a little bit of extra time. And so what I want to do is I want to show you where the methods of multivariable calculus lead to. The next class for a lot of people is either linear algebra or intro stats. What I'm going to do today is I'm going to give a lecture that I normally give in probability, which is Math 341, Stat 341. So you'll be seeing a 300 level class today. In a normal class, you would have already covered a lot of the material beforehand. I'm going to have to cover everything from scratch. It's going to be a little bit fast-paced. I have a good sense of timing from the guinea pigs, also known as Section 1. Okay? So the idea today is to just get a sense. Right now, we only have two real techniques for doing multivariable integration. What are our two techniques? Yes? Change of variables. Change of order. We are going to learn a third method today. The method today is integrating without integrating. Right? We will see how to actually evaluate integrals without integrating. I'm going to do this through probability. You have a set of notes which actually go through all the calculations that we're going to do on the board. Do not look at them during the lecture. I want the surprise to be surprising. Okay? So you should hopefully not see where the lecture is going. And it will hopefully be a wonderful end. So I want to start with what does it mean to be a random variable. So this is a great concept of probability. We've seen it a few times. So we say x is a random variable with density f of x if the following is true. It's non-negative, and it integrates to 1. So in particular, if I want to know what's the probability I take on a value in the interval a, b, then it's just going to be the area under my curve from a to b. So if you've taken a calculus class and your professor or teacher has never said area, they should be shot. Okay? This is why, I've never said probability, they should be shot. If they only say area, that's wrong. Why do we care about areas? Areas are probabilities. So some notation. I use the little subscript x to remind myself that this is the density associated to the random variable x. We are going to have a huge number of random variables playing roles today. And it's going to be hard to keep track, so the subscripts are really good. In calculus, you often use capital letters to denote antiderivatives. So the big F over here is the antiderivative of the little f. It's called the cumulative distribution function. So big F of little x is the probability my random variable takes on a value at most little x. So it's the same as integrating from negative infinity to x of my density. Well, I can't use the letter little x now, so I use t as a dummy variable. So it's going to be fx of t dt. And so by the fundamental thing of calculus, or just by the rules of integration, if I take the derivative, I'll get the value of my integrand at the point x. So the derivative of my cumulative distribution function is my density. Okay. So what I want to do now is I want to start and I want to introduce a very useful function. And this function will play a key role in all the stuff we're looking at later today. So it's the gamma function. And we've seen a little bit of it already. So gamma of s is the integral from 0 to infinity of e to the negative x to the s minus 1 dx, at least if the real part of s is greater than 0. If you don't want to work with complex numbers, just let s be a real number, but it turns out this function exists more generally. This is a very useful function. In a normal 341 class, you would have already seen it, and we wouldn't have to detour and talk about some of its properties. But this is going to allow me to review some Calc 1 and to review some techniques. So the first thing is, whenever you get an integral like this, you want to ask, does it make sense? Does it exist? Is it defined? Well, the integrand is non-negative. That's good. So there are really only two things to check. How is it behaving near 0, and how is it behaving at infinity? Is it decaying fast enough at both of those places so things are fine? Well, I have exponential death. I have polynomial growth. Exponential death beats polynomial growth. Let me show you why that's true. I'm going to do the proof for a specific value of s. Let's say s equals 2018. Right? I know e to the x is greater than or equal to x to the 2020 divided by 2020 factorial. And this comes from the Taylor series. Have you seen Taylor series for e to the x?
Yeah.
Okay, great. So I'm looking at just one term, and since x is non-negative, if I take just one term, it's going to be a lower bound. So now if I just flip the sides, I get 2020 factorial over x to the 2020 is going to be less than equal to, I'm sorry, it's going to be greater than equal to e to the negative x. And if I multiply both sides by x to the s minus 1, so x to the 2017, this is still going to be true. And now if I integrate this from 1 to infinity, I see that this integral is going to be less than equal to this integral. Well, this looks like 1 over x cubed. 1 over x cubed is integrable, as long as I don't go all the way down to 0. So this is finite. So what this is telling me is I have enough decay that this integral is not a problem for large values of x. I now have to show it's not a problem for small values of x. All right? So now we need to look near 0. So near 0, what's the largest e to the minus x could be? 1. So the best thing for us is if x equals 0, it's 1. And as x gets larger, e to the negative x gets smaller. So we have e to the negative x, x to the s minus 1, is less than equal to x to the s minus 1. So if I integrate this from 0 to 1, that's less than equal to the integral of this from 0 to 1. And now I just want to know, when is this integral well defined? So for this integral to be well defined, I just need the exponent of x to be greater than negative 1. If I have x to the negative 0.9, when I integrate that, I would get x to the 0.1. If I have 1 over x, however, the integral of that is logarithm of x, and when I plug in 0, I get negative infinity. So as an exercise, I'll let you just check and make sure that you're okay if the real part of s is greater than 0, because then the exponent of x will be greater than negative 1. And so the integral is well defined. So this is a function we can look at. We can start calculating some values. Gamma 1 is 1. Gamma 2 is 1. So maybe it's always equal to 1. In a real class, I would slowly go through this and do the calculations, saving time. Gamma of 3 is 2. All right, it's 1, 1, 2. Maybe it's the Fibonacci numbers. Let me do some more calculations. Gamma of 4 is 6. Gamma of 5 is 24. Anybody want to hazard a guess on the pattern? Yes?
It's like it's multiplying in sequential order. So
Yeah.
multiplying by 1, then 2, then 3, then 4.
Yeah, so what numbers are these? You've got it. There's just a special name for these numbers. If you're really excited, you can put an exclamation point in your answer. The factorials. This is 0 factorial. This is 1 factorial. This is 2 factorial. This is 3 factorial. This is 4 factorial. So it looks like gamma of n is equal to n minus 1 factorial. So it turns out this is called the functional equation. So gamma of s plus 1 is s gamma of s. I'm not going to prove that. So, again, I strongly urge you to do this. The proof is you integrate by parts. So there's only 2 homework problems, I believe, for Monday, and they're both optional. So the homework is out of 0 points. Okay, so whatever you get is just going to be added to your homework average. This is deliberate so that you have time, if you want, go through and do all this stuff. This is a great way of reviewing your Calc 1. A lot of people had trouble doing some of the integrals. Today's lecture is giving you, here's a bunch of integrals that are worth doing. These are not tedious integrals. These are integrals with meaning. Okay? So if you integrate by parts, you get the following. So using that, we would get gamma of n plus 1 would be n gamma of n. Well, by induction, if we know gamma of n is n minus 1 factorial, you get n times n minus 1 factorial. Have you seen factorials?
Yeah.
Good. So this would then just be n factorial. So Can somebody give me an interpretation of what does 3 factorial mean? You know, what is 3 times 2 times 1? What does that mean combinatorially? I know it's 6, but can you give me a meaning?
It's like if you're picking things out of a box, it's like you have 3
Good.
choices and you have 2 choices.
Good. So if I have 3 people, there are 3 factorial of 3 ways to arrange 3 people when order matters. Now what's nice about this function is this gives us a generalization of the factorial function to other values, to values that are not integers. You have seen stuff like this before. You know, when we did the geometric series, 1 plus x squared equals 1 over 1 minus x, at least if the absolute value of x is less than 1. This only makes sense if the absolute value of x is less than 1, but this critter on the right makes sense for every x other than 1. It extends. It turns out it's remarkably useful to be able to extend. Now, one of the most interesting places to extend this to is the following. We say x is a normal variable with mean 0 and variance 1, or call it the standard normal, or we sometimes call it the Gaussian. If the density of x is 1 over square root of 2 pi e to the negative x squared over 2. So it has mean 0, variance 1. Standard normal, very important in statistics. Because it's a probability distribution, what 2 things must be true? Got to answer faster. We're not going to make the lecture today. What 2 things must be true? Has to be positive, or at least non-negative.
Yeah, non-negative.
Yes. And it has to integrate to 1. So remember, we did that beautiful polar trick where we squared the integral and we went to polar coordinates and we used multivariable calculus to evaluate a one-dimensional integral. Nice, nice backdoor. So we know the integral from minus infinity to infinity of fx of x dx equals 1. Using this fact, you can actually get gamma of 1/2 is the square root of pi. That's how you should view the square root of pi down below. And the proof is a change of variables, let u equal x squared, and du equal 2x dx. I am not going to do this calculation. I'm going to leave this as one of the calculations for you to do. I strongly urge you to show how you should play change of variables and get, because the standard normal integrates to 1, gamma of 1/2 is equal to the square root of pi. Does everybody agree that I can write 1/2 as negative 1/2 plus 1? So according to my rule, I will put this in quotes. This is equal to negative 1/2 factorial. So if you happen to have negative half of a person and want to know how many ways you can arrange them, there are square root of pi ways to arrange negative half of a person. Right? This is known as bullshit. Okay? The combinatorial interpretation no longer holds. Right? I want to be very careful when I'm talking about negative half of a person so you don't saw somebody in half and try to, okay? There's no way you're going to have negative half of a person. So what the hell do we mean? Well, we have a function that agrees with the factorial function at positive integers, but does some strange stuff in other places. All right. So now that we have the gamma function, we're going to use this to define a new distribution. It's going to be called a chi-squared random variable. So the only random variables we're really going to look at today are the normal and chi-squared. We're going to see that there's connections between them, and by looking at them, we are going to review a lot of the concepts we've been looking at this semester, as well as see some incredible applications at the end. So we say x is a chi-squared random variable with k degrees of freedom if the density function is equal to 1 over 2 to the k halves gamma to the k halves e to the negative x over 2 x to the k minus 1 if x is greater than or equal to 0 and 0 otherwise. Okay, so you've got to be careful as to where you put all your factors. This is the nice thing about doing it twice. Okay, all right. Did I make a mistake? I think I did make a mistake, actually. Yes, this should be k over 2. Because unfortunately, there's a lot of different ways you can define things. If you look at this, everything seems to be depending on k over 2. Why don't we call it a chi-squared random variable with k over 2 degrees of freedom? It turns out it's more useful to look at it as a function of k. If you go back a moment ago, we had gamma of n plus 1 is n factorial. This seems to be another example from the people who gave us 1 over cosine is secant, and 1 over sine is cosecant. It looks like it's bad math notation. Why would you define the gamma function so gamma of n plus 1 is n factorial? Why not have gamma of n be n factorial? One of two things must be true. Either mathematicians yet again don't care about good things, or there's another place where the gamma function emerges, and this is the better definition. And that's what's going on. It's that other application, that other beginning, which is the reason why it's defined this way. So over here, it turns out it's better to view this as k is the parameter, even though every place that matters, it's k over 2. So because this is a probability distribution, what two things must be true? Positive. Oh, no, we did it again. Non-negative.
Non-negative, and then integrate.
And then integrates to 1. So we need to show that this integrates to 1. Well, I have a gamma here. I've got a gamma over here. The proof that it integrates to 1, let u equal x over 2. And just change variables, show that it's equal to a gamma function, and then do all the algebra. I strongly urge you to do this. Okay, these are all one-dimensional integrals, but they're ones that are worth doing. And so when the dust settles, you will see that this is a new probability distribution. And we have the following remarkable theorem. If each xi is a chi-squared random variable with ki degrees of freedom, and they're all independent, then x1 plus xn is a chi-squared random variable with k1 plus kn degrees of freedom. So a sum of chi-squared random variables, if they're all independent, is a chi-squared random variable. And what's the parameter? It's the sum of the parameters. Things behave very nicely. Okay, so I want to prove this. To prove this, I'm going to have to introduce some techniques from probability that have nice applications in multivariable calculus, and it will allow us to review some things I care about. All right? We're also going to review one of our old concepts. So in Calc 1, you prove that the derivative of a sum is the sum of the derivatives. That's only if you have two functions. Does anybody remember how we then got the derivative of a sum of three functions is the sum of the three derivatives? Yes? By grouping. Excellent. We're going to do grouping again. All we have to do is show that the sum of two chi-squared random variables is chi-squared. So proof by grouping. So if we have x1 plus x2 plus x3, we first group these two together. And then that will be a chi-squared random variable with k1 plus k2 degrees of freedom. This will be a chi-squared, and now we'll have a sum of two chi-squareds again. And that will give us the sum of three chi-squared random variables. If we then wanted to do 4, we would group the first 3 together. If we wanted to do 5, we'd group the first 4. And so it's induction. Again, all that really matters is doing the step when we have just two chi-squared random variables. So as long as we can do it for 2, we can do it for anything. So the technique we're going to use is called convolutions. And this is a type of integration that is worth knowing. So let's say z is x plus y, and these two are independent random variables. So imagine I'm rolling 2 die, and I want to figure out what is the distribution of the sum. There's a very nice formula for the density of z. It's the integral from minus infinity to infinity of the density of x at x times the density of y at z minus x dx. So you can see when I do the integration, I integrate out x and I'm left with just a function of z. Good, that's what I should have at the end. You could justify this using cumulative distribution functions. By this point in 341, we would already have done that. I'm going to just give you the fast and dirty proof as to why this is reasonable. Somebody give me a number. 18, good number. Okay. Which trader from the Red Sox wore 18? Trader. Nope. All right. So if I want z to be 18, I look at all the pairs of x and y that can add up to 18. Right? It could be 17 and 1. It could be 15 and 3. Right? It could be 0.1 and 17.9. This is essentially the probability I get x. Well, if I know that the first one equals x and I want the sum to be z, what does the other one have to be? It has to be z minus x. So I look at all pairs. This is essentially the probability I have that pair, and then just integrate over all possible pairs. So we often write this as fz of z is fx star fy, because this occurs so many times in mathematics. Well, this better be a probability distribution. So if it's a probability distribution, what must be true?
Non-negative.
Non-negative,
And integrates.
and it integrates to 1. The non-negative is not a problem. I have two functions that are non-negative. I multiply them and I integrate. Can't become negative. I now have to show that it integrates to 1. So if I integrate z goes from minus infinity to infinity of f of z dz, this is the integral. Z goes from minus infinity to infinity. Then the integral x goes from minus infinity to infinity of fx of x, fy of z minus x, dx dz. So I have a double integral to do. How should I evaluate a double integral? What technique can I use? We only have two. Change of order. There's nothing else we can do. There's really no good change of variables here. Let's change the order of integration. So this is the same as x goes from minus infinity to infinity. This has no z dependence, so I can put that outside the z integral. And you can see how many of our concepts we're reviewing today by going through this. Okay? And then I have the integral z goes from minus infinity to infinity of fy of z minus x dz dx. Well, let's look at the second integral. So z goes from minus infinity to infinity, and for each z I'm just subtracting x. So as z ranges from negative infinity to infinity, what does z minus x range from? You have fixed x. What does z minus x range over? Yes? Negative infinity to infinity. So if I just do a u substitution, if I let u equal z minus x, du will just be dz, and we get it's the integral x goes from minus infinity to infinity fx of x, and then the integral u goes from minus infinity to infinity of fy of u. It's very important that I have the subscript y. Fy of u du dx. What's the integral of fy of u du? 1. It's a probability distribution. This integrates to 1. And now I'm left with the integral of x from negative to. What does that equal? 1. So that proves, I'll put in the little box to say end of proof. That proves it's a probability distribution. It integrates to 1. So the convolution is a really nice way, if you have the densities of independent random variables, you can calculate the density of the sum. All right. The warp speed lecture continues. All right. We have the proof by grouping. We have the definition of a chi-squared random variable. We now want to prove this theorem, so all we have to do is prove it in the special case of two chi-squareds, and we have to calculate what is their density. So we're going to use the convolution, and we're going to use it for a very specific choice. Okay. And this will lead to our first non-trivial example of a new method. Okay. So now, xi will be chi-squared with ki degrees of freedom. So we will let z be x1 plus x2. So the density of z is going to be the integral x goes from minus infinity to infinity of the density of the first one at x times the density of the second one at z minus x dx. All right, but we have a chi-squared random variable. So for chi-squared random variable, what's the smallest input where the probability has a chance of not being 0? So when you look at the density, I claim that for certain values of x, we don't have to worry about the probability. Which values of x don't we have to worry about? Where's the density 0? For what values of x is the density 0? Well, infinity, but that's beyond our point of integration. For what values of yes? Yeah, when x is negative, the density is just 0. The density is this if x is non-negative. The density is 0 if x is 0. So when I have, so I have to yell. When I have to integrate from negative infinity to infinity, I really don't have to go all the way from negative infinity. Where can I start? I can start at 0. All right. Halfway there. Okay? Who sings Living on a Prayer? All right, there we go. Getting something at least. When you look at the second one, what does that give us for the upper bound of x? How high can x go before we no longer have to worry about things? We have evaluating it at z minus x. Yes? It can't go larger than z. Once it's larger than z, we're evaluating this at a negative number, and the density is 0. So I can change the upper bound. So now I've gone from a doubly infinite integral to an integral from just 0 to infinity. 0 to z. That's not so bad. I'm going to introduce one more piece of notation. I'm going to let ck be 2 to the negative k halves gamma of k halves to the negative 1. This is the normalization constant of the chi-squared random variable. I don't want to keep writing this every single time. It's tough enough to write it once. So what do I get? I get ck1, you're pulling out the density from this. I'll get a ck2 from the second. I get an integral x goes from 0 to z. Now the density of the first one, I have e to the negative z over 2, I'm sorry, e to the negative x over 2, x to the k1 over 2 minus 1. So I get e to the negative x over 2, x to the k1 over 2 minus 1. The second one, I now get the same thing except I replace x with z minus x, and I replace k1 with k2. So I get e to the negative z minus x over 2, and then I get z minus x to the k2 minus over 2 minus 1 dx. All right, there is some nice cancellation. E to the negative x halves, e to the positive x halves, those cancel. I can pull out an e to the z over 2. I'll get ck1, ck2, e to the negative z over 2, integral x goes from 0 to z, and then I'll get an x to the k1 over 2 minus 1, z minus x to the k2 over 2 minus 1 dx, and this is a hellish integral to do. Fortunately, we don't need to evaluate it. We can use a trick. What you want to do is you want to get a sense of what's the z dependency. I really care about the z dependence. And so I've got a z minus x. It would be great if instead of having x, I had z times x, because then I could just pull out the z. So this suggests changing variables. Let's let x equal z times u. So dx is z du. And if x goes from 0 to z, what does u go from? So if x goes from 0 to z, what does u go from? 0 to 1. All right, so now when I put things in, I'll get a z to the k1 over 2 minus 1. I'll pull out here, I'll get a z to the k2 over 2 minus 1. So I'll have like a minus 2. but then the dx gives me a z du, so I'll really have it to a -1. And when the dust settles, you can trust me on the algebra. I did it last night. I did it again about an hour ago. We get the following. We get our density function is equal to ck1, ck2, e to the negative z over 2, z to the k1 plus k2 over 2 minus 1. And then we have the integral u goes from 0 to 1 of u to the k1 over 2 minus 1, 1 minus u to the k2 over 2 minus 1 du. This is still a nasty integral. Especially if k is an odd integer, then you've got square roots. But we don't need to evaluate it. This is some number. Do you agree that this is just a number independent of z? There's no z dependence. I'm integrating out u. It's a number. If I give you the function f of x is x log 5, don't use the product rule to find the derivative. It's the constant rule. Log 5 is a number. This is a number. Let's call it I, k1, k2. It's just some number. So this is ck1, ck2, I, k1, k2. And then I have e to the negative z halves, z to the k1 plus k2 over 2 minus 1. I know this is a probability distribution. And if you look at how it depends on things, it looks exactly like a chi-squared random variable. I have a negative z halves, and I have a z to the k1 plus k2 over 2 minus 1. It looks like a chi-squared random variable with k1 plus k2 degrees of freedom. Because this has to integrate to 1, I know this integrates to 2 to the k halves, gamma k halves. So what that means is, since this is a probability distribution, this integrates to 1. So this whole thing here must be c k1 plus k2. That's the only thing it can be, because it has to integrate to 1. This is integrating without integrating. And so now we've seen that it is a chi-squared random variable. So this proves that x1 plus x2 is chi-squared with k1 plus k2 degrees of freedom. And what's nice is the functional form, how it depends on z, we can now figure out what that integral is. Okay. Any questions so far? All right. So now we need even more material. The other big function is the normal. Okay? So we've just shown that sums of chi-squared random variables are nice. It turns out that chi-squared random variables are related to the normal random variable. And there's the following beautiful theorem. If x is a standard normal random variable, so this is our Gaussian, then x squared is a chi-squared random variable with 1 degree of freedom. Right? We're going to quickly prove that. So the cumulative distribution function for my random variable x squared at some point, I'll call it z, this is just the probability that x squared is at most z. This is the same as the probability that negative square root of z is less than equal to x is less than equal to square root of z. If my square is at most z, then my square root has to be between negative square root of z and positive square root of z. So this is going to just be twice the probability that 0 is less than equal to x is less than equal to square root of z. So this is just twice the antiderivative of my density of the standard normal evaluated to square root of z minus twice it at 0. And now the way you get the density is you take the derivative of the cumulative distribution function. So we get the density of the random variable x squared at the point z is just twice. Now I take the derivative of this and I use the chain rule. So I'll have the derivative of my density at square root of z times the derivative of z. So there was an extra credit problem on this that, some people tried, and you have to remember that you have to take the derivative of the inside. It's a chain rule. What's the derivative of this piece with respect to z? 0. It's a constant. So now I just get I get the density of the standard normal evaluated square root of z, and then I get 1/2 z to the minus 1/2. I'm not going to do the rest of the algebra. We don't have time. But you can see that it's at least reasonable. I'm taking the density of a Gaussian, and so remember the Gaussian density, it's 1 over square root of 2 pi e to the negative x squared over 2. Because I'm evaluating the square root of z, when I square, I'll get e to the z over 2. Okay. It is beginning to look like the chi-squared random variable. Okay? So the square of a chi-squared random variable is going to be a normal. Sorry, other way around. The square of a normal random variable, a standard normal, is going to be a chi-squared random variable with 1 degree of freedom. So there's a relation between these random variables. Okay, why do we care about all this? Well, we just showed that the sum of a chi-squareds is a chi-squared. So what this tells us is, imagine we sum a bunch of squares of independent normals. So let's say each xi is normal with mean 0, variance 1, and they're independent. So then if I look at x1 squared plus xn squared, this will be a chi-squared random variable with how many degrees of freedom? So how many degrees of freedom? N. Each one of these is a chi-squared with 1 degree of freedom. We have n of them, so this will just be n. Yes?
Wouldn't it be a minus 1?
Nope. So we just showed that a chi-squared, that if you square a normal, it's a chi-squared with 1 degree of freedom. So if I sum 2 chi-squared random variables, the degrees of freedom just add. So since I have n of them, it will be that. Now, the place where you have the n minus 1 is with the factorial. Your gamma of n would be n minus 1 factorial. But here it will just come out as a n. So this is fast. You haven't been looking at the stuff beforehand. This is not material we're going to use later in the semester. This is just to give you a sense of where things go, so you can try to figure out, if you're interested in this, do you want to take Stat 201 before linear algebra? Do you want to try to go straight into probability and not do linear algebra? Not advised, but it's possible. Do you want to just have these in the back of your mind? Where do we use this stuff? Why do we spend so much time on integration? And so this is fast, but because it's a chi-squared, we know the density, if we call this z, the density of this function, and you will see later why I want to use the letter r, is just going to be my normalization constant, which will be 2 to the negative n halves, gamma of n halves to the negative 1, e to the negative r over 2, e to the negative r over 2, and then r to the n halves minus 1. So that will be my density. So if I sum n squares of standard normals, it's going to be a chi-squared with n degrees of freedom. Okay. When you see a sum of squares like this, does that remind you of anything? Any thoughts on where you might see that? Right, so we'll wait a second and it'll become a little bit clearer. We've had this on the board long enough. I'm going to take the space back. So let's study the sum of these squares another way. And this will get the surprising result at the end. So let's let z be our x1 squared plus xn squared, all are normal random variables. They're all independent. So if I want to look at the cumulative distribution function, this is the probability that big Z is at most little z. This is the probability that x1 squared let's use the letter R. Plus xn squared is at most little r. So when you see your x1 squared plus x2 squared plus dot 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 is less than or equal to r, what are you thinking of geometrically? What kind of shape would this be? X1 squared plus x2 squared plus dot 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 plus xn squared is at most r. Yes? Not a ring, close. Let's do it in small dimensions. Let's say I give you x1 squared plus x2 squared is less than or equal to r. What kind of shape is that?
Circle.
Circle. x1 squared plus x2 squared plus x3 squared is less than or equal to r. What kind of shape is that? Sphere. This is a sphere in n dimensions with radius square root of r. Wonderful. All we have to do is generalize spherical coordinates to n dimensions. Right? So that means we'll have to figure out what all the angles are, what the ranges of the angles are, and then what the Jacobian is. So that means we'll have to calculate the determinant of this n by n matrix. Or we can do a backdoor and integrate without integrating. And so I'm going to show you the backdoor. So this is the same as the integral over x1 squared plus xn squared less than or equal to r. Now, the density of these is 1 over square root of 2 pi e to the negative x squared over 2. So when I substitute, I have 1 over square root of 2 pi n times. So I have 2 pi to the negative n halves. The exponentials will become x1 squared plus xn squared over 2 dx1 through dxn. All right, we ready for the generalized spherical coordinates? No, we don't want that. dx1 through dxn. What does that go to? So what power of the radius must I have in my n-dimensional coordinates? It's a really good question.
2x.
So I need to know what's the power of rho. Yes?
Is it just n?
It's not n. It's
N
n minus 1. Because remember, the radius, the d rho, that's going to be in meters. But then the d of all the angles will not be in meters. So I need a rho to go with each angle. So I know whatever the change of variable is, it's going to be a rho to the n minus 1, some horrible function of the angles, and there'll be n minus 1 angles. And then we'll have a d rho, d phi 1, d phi n minus 1. Things I am not doing. I'm not saying what this is. It's in the notes on the bottom if you want to see exactly what powers of sine, and if you want to see what the ranges of the angles are, and what the different variables, it's all there. It's not necessarily the standard notation I would use, but it's a valid choice. We are going to solve this problem without knowing what g is. When you look at this, does this function have any angular dependence? And that's the miracle. Because it has no angular dependence, this is the same as the integral of 2 pi to the negative n halves. Then we'll have an integral. Rho goes from 0, and then what's the largest value of rho? How high does rho go? It goes to, not to r. It's a sphere, and what's the radius of the sphere? Square root of r. So rho goes from 0 to the square root of r. Then we will have an e to the negative rho squared over 2. Then we'll have a rho to the n minus 1. We'll have a d rho. And then we'll have all the angular crap of g phi 1 to phi n minus 1, d phi 1 to d phi n minus 1. Okay? When we integrate this, this integral has no angular dependence. So you can view this as it's constant on the surface area of spheres. So when you're doing this integration, you will get the surface area of the sphere in n-dimensional space. So this integral here, I'll call it an minus 1. Or if you want, you can call it, the notation is debatable, so you want to call it n minus 1 or an. I'm doing n minus 1 to just remind myself it's a lower dimensional object. It's the surface area of the n sphere in n dimensions. And so I don't need to know what g is. I just know this has to integrate to 1. It has to integrate to the surface area. Because this function here has no angular dependence. So I get that this is equal to 2 pi to the negative n halves, a n minus 1, and then the integral rho goes from 0 to square root of r, e to the negative rho squared over 2, rho to the n minus 1 d rho. All right? This is the cumulative distribution function. Okay? So if you want, let this function here be g of rho, and let big G of rho be its antiderivative. Okay? So you get that this is equal to 2 pi to the negative n halves a n minus 1, and then you get g of square root of r minus g of 0. And now I take the derivative. This is what fz of r was, the cumulative distribution, big F. So the little f, the density, is the derivative. So I get 2 pi to the negative n halves a n minus 1. Now I take the derivative of g, so that'll just be little g of rho. And now I have to take the derivative of square root of r. Well, that's just going to be 1/2 r to the negative 1/2. And what's the derivative of g of 0? 0. It's just a constant. All right, so we get that this is equal to 2 pi to the negative n halves a n minus 1 g of, I'm sorry, I should be evaluating this at square root of r. So then I get e to the negative r over 2. Then I get a square root of r to the n minus 1. So that's an r to the n minus 1 over 2. And I have an r to the negative 1/2. And I have a factor of 1/2 over here. So that's my density. And not coincidentally, I did not erase the density over here. This is the density I get when I use the fact that the sum of the squares of the normals is chi-squared with n degrees of freedom. We calculate it another way. This is one of the most powerful techniques we have in mathematics. Do something 2 different ways, and if you haven't made a mistake, they're equal. So we also get fz of r is equal to 1/2 2 pi to the negative n over 2, a n minus 1, e to the negative r over 2, and then an n minus 1 over 2 and an minus 1 over 2 is just r to the n over 2 minus 1. Same. These must be the same. So we get that 2 to the negative n halves, gamma of n halves, is equal to 1/2 2 pi to the negative n halves a n minus 1. Or solving a n minus 1, the 2 to the negative n halves cancels with the 2 to the negative n halves. We get the 2 comes over. We get a pi to the n halves. We divide by gamma of n halves. We have just calculated the surface area of the n-dimensional sphere. What should you do now to see if this result is reasonable? What could we do? We're like half a minute in front of section 1, so we have time for this. I'm giving you this formula. What could you do to see if this formula is reasonable?
Check the surface area of a sphere.
Yeah, check the surface area of the sphere. Check n equals 2, n equals 3. Check the cases we already know, and see if you get the right answer.
So where did the gamma to the n over 2 to the...
Oh, sorry. This should be to the negative 1. Sorry. I dropped the negative 1. So now that we have the surface area, we can actually calculate the volume as well. And so I will just quickly end with the volume calculation, and then that will be a good place to stop. So if I want to calculate the volume of the sphere in n-dimensional space, right, with radius, say, big R, this would just be the integral rho goes from 0 to big R of the surface area of the n-dimensional sphere times rho to the n minus 1 d rho. So you get a n minus 1 r to the n over n. When I put in what things are equal to, I will get 2 pi to the n halves over n gamma of n halves. I can take the 2 upstairs and move it downstairs. This is the same as pi to the n halves over n halves gamma of n halves times r to the n. And then this just simplifies as pi to the n halves over gamma to the n halves plus 1 by the functional equation of r to the n. There is the formula for the volume. We got the formula for the surface area and the volume without writing down what the spherical coordinates are. The key idea is that we have a probability distribution. The integral of a probability distribution is 1. If you know that, then whatever you can't integrate, if you can integrate everything else, then whatever's left over must be the constant you need to make it integrate to 1. So we reviewed an incredible number of techniques today. We saw an application of switching orders. We saw connections between antiderivatives and functions. The antiderivative is the cumulative distribution function. Its derivative is the density. We saw integrating through convolution to give us connections with probability. We saw that certain random variables are connected to other random variables. The square of a normal is a chi-squared. If you think of the method of least squares, when we sum the errors, if the errors are normally distributed, we're now summing squares. This tells us that the error in the method of least squares should be a chi-squared random variable. And this gives you some idea of understanding when fits are good. So again, huge amount of material today. This is to really show you where the major goes in either math or stats. You are trying to decide in the very near future. I am happy to chat with you about what course might be appropriate. Have a good day. Recover. Enjoy the weekend.